Um, Good afternoon, everybody. I'm Christos Argyropoulos. I'm one of the academic physicians at the University of New Mexico. I'm one of the faculty who's responsible for the service course, which includes informatics services for the Clinical and Translational Sciences Center at our university. And today I'm gonna be staying in the general space that Brent started with his OpenMP and C and talk about foreign application memory management using Perl. I have no disclosures for this talk. Um, for today, my talk has four objectives. First, to review the rationale of a module called Task uh, Memory Manager, which is a new module for managing raw memory in Perl. Discuss strategies for managing memory using native Perl and the Perl API. Those are effectively the implementation behind Task Manager. Present some performance data about alternative memory allocators and managers, and finally illustrate the use of the package for multi-language applications. A major impetus for doing this is my own work, which involves cross-language applications, and we'll talk a little bit about that during the talk. So why care about memory? Well, memory is really everything in modern computer architectures. So the von Neumann architecture, which is the architecture used for in every computer since the late 1940s, has the memory as a central component. In fact, the presentation of the patents of the first processors did envision that there would be a control unit that inside the CPU that sort of shifts the memory or shifts attention of the processor to different parts of memory, some of which are contain instructions, others which contain data, and it's through memory operations that our computers work. More relevant to the conversation in this century as opposed to last century, in modern processors, it is the speed by which we move stuff in and out the main memory that determines the speed of programs. Our processors are powerful enough to be able to execute many and complex instructions per cycle. So in that environment, it is the speed by which you move things in and out of memory that determines the final performance. Yes. What What about now? Hmm. Let's see if I can do that because it's like I'm not really used to Google Meet. So slide sorter, slide master. Yeah, that's what I did. Mm, a window. No, just one monitor. No, we just have to figure out how to do this. It's just that I don't present it. Wait a second. What about now? Yeah, Wait. A little bit better. Okay. All right. And let me see if I can make it a little bit bigger as a zoom. Okay. 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 All right. So, how is memory used in programs? So, programs use memory as scratchpad. They use it to communicate between processes or between threads. They use it to communicate between components written in different languages. Um, so, what these are like some of the many use cases that having access to memory regions can help you with. However, in as I said previously, in modern computer systems, memory management can affect performance. In fact, depending on the type of application you write, you may have to select a different memory allocator or memory manager to ensure that your speed is optimized. All textbooks in particular, and that includes many of the Perl documentation, warn against combining memory managers. So, if you're using something like sysmalloc, you should not be using a different memory allocator in the same application. For example, gmalloc, which is one of the uh, more recent and performant ones. However, this is really like a relic from the era where memory was shared as absolute addresses. Nowadays, modern operating systems and processors use hashes and memory management units to ensure that the memory is served as logical addresses. So, in a given application, you can actually combine memory that's released or allocated through different data structures. And I really wanted to like emphasize this point because if you read the Perl API, there is like a big warning that just use our own memory allocation functions, don't mix it with everything else. But this is really not something that is a valid warning nowadays. So, how and why did I write this package? As I said, I needed a flexible approach to manage memory for my research work, which involves writing components in other languages, mostly C, less likely Fortran, and increasingly assembly. Um, I needed to combine allocators for different use cases, including multi-threaded code with OpenMP. Allocating memory for multi-threaded applications has to consider what's called the first touch policy by the operating systems, which means that when you allocate memory inside a thread, the memory will be allocated closer to the physical core that executed that thread. Not all memory regions are equally accessible from all the cores because of the delays in electrical submission inside our motherboards. So one needs to be aware that for a particular multi-threaded application where you allocate memory will exchange performance. Um, Perl is actually my go-to language for the highest level of abstraction in applications. I don't really use Python. I kind of didn't like it when I got exposed to it. And while I'm a heavy user of R is kind of limited as a sort of a workflow and data flow language. So in summary, I needed a way to support multiple allocators to cover different use cases in my programs. To prevent memory leaks, I needed to have a tight life cycle management. which in this case means that I had to be able to support immediate, delayed, or on-demand deallocation of memory or garbage um, collection. Um, so, how do you allocate raw memory buffers to pass around using Perl? There are three main options. The first option is really portable. You can use buildings from inside Perl and some functions that you find in various Mega CPAN modules. In fact, you can, like a standard Perl string is a good way to allocate a buffer. Then you have partially portable or non-portable options in which you use an external library and you interface with it using inline C and or FFI platypus. For this talk, my major focus will be on inline C. There are ways to do this with FFI platypus, but you probably have to wait until my talk in the summer about those. So this is an example of how one can allocate memory and pass it around using Perl. You load the module called convert scalar. There is a function there called grow. Um, so you can initialize, like you can declare your own like buffer, like in line 9. Then you can grow it to the desired size by the grow function. And then you can use the vec function to sort of modify bytes inside that memory region. So this is like one good way of doing this if you didn't want to bother with any of the stuff I'm going to talk about. You can grow your buffer, play with it using vec, and then pass it around in functions if you would like. Interestingly enough, if you are doing this and you would like the region to remain in the same physical address of memory or the same actually logical address of memory, you should not write past the end of the region once you have allocated it. If you do, then Perl will likely go and reallocate the buffer and your program will suffer a performance hit. So this is an example of how things look like in memory. So you can, once you can use develop peak to look at exactly the size of the buffer that's allocated. In this case, I declare the buffer. Its scalar value is found on this address in memory. Then I can grow it to the desired size. As you can see, the buffer changes from null to pointer value, which basically it's the location in memory where the contents are contained. I can go and change a single byte inside the buffer. So you can look at the size. The pointer value here is where the memory is located. And I change it to the letter A. And if you print out as in bytes, you can see that the letter A appears there. And but if you grow the buffer past its end, which you can do so by appending different characters, then the entire thing goes and becomes relocated to a different address. Note that the address here is different than the address there. Another good way of allocating buffers is through the vec function itself. You can call vec. The first argument of vec can be a scalar value. You can set a desired size, and then you can allocate everything and initialize them to 0. And when you dump the content of this str variable, you can see again the same thing, that vec gave you access to a buffer that you can now use for whatever you want. There are a few other options which are available. You can actually use the pack function to do something like that, Or if you're really lazy and you don't want to mess with a lot of complicated things, you can simply take an out byte or a byte value and then initialize it as a string. So, you use the concatenate operator to effectively, or actually the multiply operator for strings to give you a buffer of the desired contents and length. And for the most part, I think people are in generally aware that these are the tricks that you can use to allocate some memory that you can then play with VEC and the other functions of found in Perl. Interestingly enough, you can use the inline package to allocate memory, effectively taking over the memory allocators that the Perl API uses to get a hold of a buffer that you can use for your own purposes. So the program to do so is extremely easy to write in C. And I have the C code on the right hand side. You write a function that effectively allocates a scalar value, um, which which is used to hold the memory address of the buffer. So the code itself calls the newX function. This is used to allocate an array of a given length and type of character, meaning bytes, and then you can return back to the Perl program the integer, an integer value, which is the logical address of the array. Uh, the Perl API has another function called new XZ, which basically returns you a zero allocated memory space. And, you include those inline functions. And then on the C side, and then on the Perl side, you just, call them and you get the address of a buffer that you can use around. So what exactly does this construct use? So the rationale behind this is that we jump from Perl into C and we call a memory allocator that returns the beginning address of a memory buffer. Then we wrap this memory buffer into an integer type in Perl. And then we use this integer type when we would like to sort of pass memory regions in foreign code. People who are familiar with C will recognize that this is the use case of the U in PTR type, which is a built-in type in C99 and higher that allows you to move around pointers as integers. It's actually considered the safe way to move around pointers in C as integers because you are given with guarantees of size. The C standard specification actually does not guarantee that a given pointer will always have the same type, but the same length, but UNPTR is guaranteed to be long enough to contain any pointer size that you want. So effectively, what you end up with is that you can actually recapitulate this behavior in Perl, grab a hold of an integer that stands for the beginning of a memory region and then pass it around. And this pattern is really what is used to drive memory allocation in Task Mem Manager. Now, having figured out how to do this using the Perl's memory management routines, you can actually extend this to uh, any any memory allocator really, because what you need to do is go and call the function that gives you a hold of memory, take the beginning address of the memory, and then send it back to Perl. So in this case, I've done this with the calloc, which is an allocator that's available to C programmers. But in theory, any library that gives you access to a memory address will allow you to do this allocation. Now, the reason that you would like to play with different allocators is because there are differences in how fast memory is released back to you. As I said, modern allocation in our operating systems does not really give you the memory immediately. It gives you a guarantee of a memory access, and it's only when you actually go and read or write the memory region that the operating system will release the memory to you. So if you're writing a big application in which you want to pre-allocate memory, which is then used on demand, then how fast you allocate the various memory buffers will determine how quickly you can enter the really important part of your code. So these are some memory benchmarks in which I benchmark how long it takes to allocate the buffers of different lengths from 100,000 bytes all the way to 100 million bytes. And we generated some statistics over 100 representations. And as you can see, um, if you are just looking at the speed of allocation, meaning how fast you can get the operating system to give you a guarantee that you will have access to that memory, you can actually generate buffers very, very quickly, up to 100,000 or a million buffers per second on my double core and aging Xeon. However, once you go and actually access the memory, then the speed will tremendously go down, because then the operating system will trigger memory page faults, and the allocation will actually happen at the time. So based on these results, for example, you can, if you just wanted to generate the scratch pads and then which are then accessed on demand, you can use it very quickly with the memory allocators in the Perl API. But if you wanted to initialize these regions to zero, then you can get some performance by using the zero allocators, either the Perls or the Cs. But if you try to use any of the other constructs, like trying to touch memory every, for example, 4,000 bytes, you're going to suffer a major performance penalty. So again, this is like follows the general principle that in the context of modern lazy memory allocation, if you start allocating and touching stuff before you need them, your performance, application startup time will suffer for no good reason. Interestingly enough, you can do something similar with these are also thrown for good measure, how you can actually use various Perl buildings to allocate memory. And as you can see, things like the grow is a very good way, a very fast way to allocate memory. But these like idiomatic ways to allocate memory are probably not as fast as actually going and reaching inside the Perl API. However, if for whatever reason you didn't want to mess with them, those are available to you. So, how does this knowledge is used in memory manager? So, the driving the driving principle here is that memory management is a very serious deal. So you would like to separate the various tasks, subtasks of these tasks. You would like to separate the use of a given allocator to give you access to memory, because different allocators have different performance characteristics depending on how frequently and how large you allocate in the allocate memory. You would like to use fully encapsulated objects on the Perl side to hold that memory, because the last thing you want, is recapitulate the unsafe memory access in some languages like C. So you would like to totally encapsulate the memory address that you pass around. You would like to avoid memory leaks. So you would like to have a distractor that once the object or the Perl variable that holds the address goes out of scope, the memory gets deallocated so that it can be reallocated by the memory manager. Depending on your workflow, you would like to introduce or implement a delayed or on-demand deallocation uh, functionality. Perl has a a reference counting approach to managing memory, which means that if the reference counter of a given object goes out of scope, then the region is released back. That may not be the behavior you want, as for every memory buffer you are allocating to use with components written in other language. At the same time, you would like to have the option at any given time in your Perl application to go and like get rid of scratch pads that are no longer needed. And in that case, you would like to sort of be able to convert Perl's reference counting mechanism into an explicit garbage collector. So these are like things that you can actually implement quite easily with Task Mem Manager. So the package on its version 0.02 has about 7 public functions. Then you allocates a buffer using a specific allocator. For this version of the package, we are using either the Perl API or the standard C allocators. Then we have a function that allows us to extract the buffer region. So basically, it returns you like the coordinates of an area in memory that you can then inspect as a Perl string. Um, Get buffer gives you the address, the memory address of the buffer, and that's what you use to interface with other languages. And then you can get the size, the number, the element, the size of the element stored, because the approach we took there is that you don't allocate just bytes. You can allocate objects of a given size, the number of elements, and since the package supports delayed garbage collection, the objects that the user has marked as needing to stay around and not deallocated when uh, Perl object or the Perl variable holding their address goes out of scope. So the constructor is a really simple one. It tells the module that you would like to allocate an area of memory that can hold the next number of elements of a given size. And then it uses an a reference to a hash of options that specify the name of the allocator, whether delayed garbage collection should be implemented, initial values, and a death stub, which allows you to do things like execute a given function when a memory region is released back to the operating system. So under the hood, this is a standard inside-out object. So you have various hashes that correspond to the different properties. What the allocator does is it uses the bless anonymous scalar to return not the memory itself, but an anonymous reference to the variable that holds the memory, and this is used for security purposes. In fact, for some applications like gaming applications, it's not unusual to encrypt memory pointers. So if somebody wanted, for example, to encrypt all those things, it would be easy to sort of inherit from this taskman manager, right? The decryption and encryption routine, and everything that is passed around is an encrypted address. This is used in some security-oriented memory allocators, for example, and the paper has a reference to some of this work in the context of the C++ language. Now, the most interesting thing here is what happens when someone dies. So when one of those memory regions is deallocated, we have a distractor which effectively ensures that when the object goes out of scope, it is deallocated properly and there are no memory leaks. You can even do custom cleanups in addition to that. So for example, you can write a small logging function, which I actually use to illustrate these packets later on, which gives you an idea of what memory region is being deallocated. So to see, for example, what the memory allocator routine looks like, what the constructor really does inside the package. This is, for example, the memory allocator implementation for an auxiliary module that uses sysmalloc to allocate memory. It's really like a very simple module that interfaces directly with the C code, which I had shown you previously, just a call to sysmalloc. This is an example of a module like, this is an example of like allocating and deallocating memory. So I go there and allocate a scalar called memdeth, and because I intend to kill it later on, and as you can see, the death stub here is really a login function that tells you which object is being destroyed. Then I allocate another variable called mem. I assigned it an initial value of a, um, and then in line 25, I go and set this Perl variable mem to a different memory buffer. And as you can see, when you track the execution of the program, it will tell you that the mem object was allocated, um, and then that it changed. And when I set it up to a new like value, the death stub was executed, so the memory was released back to the operating system. Then we allocated a couple of other objects like the mem, def, and mem. And at the end, when the Perl program sort of concluded, you get the message that the various objects are now being destroyed. Um, it is very easy, for example, to write a function that allows you to print the area of the memory. So this is an example of writing your own rudimentary hex viewer in Perl. So once you access that memory region, you can pass it on, use the extract buffer region function that I alluded to before, and then you can print the context of memory from inside Perl. So that's like the poor person's alternative to the develop pig package. Um, this is an example of a shallow copy. In a shallow copy, what we do is we allocate the memory, then we get another variable to point to that same area in memory. So once the initial the initial variable goes out of scope, there is still a reference remaining, which keeps the buffer alive. So, that's an example of how Perl's reference counting allows Salom copying of memory buffers to persist throughout the program. Again, this is a very you can this is like a recapitulation of what Perl does with memory in its own like variables, but it's very easy to implement this in Task Manager. If you really wanted to delay allocation, but so that you can reuse maybe the Perl variable name, but still have a record of the memory around, it's very easy to do. You can actually ask the object to be created with delayed garbage allocation, which is just a flag that you pass to the constructor, as you can see in line 24. So when you execute when you execute this program, it will tell you that the memory copied object was given this address, that the copy of that was given a separate address, and that this object has had been tagged for delayed garbage collection. You can undef the object. So if you undef the object as it happens on line 39, the object actually does not deallocate it until the Perl application executes. As you can see, the output of this program, the death stamps tell you that everything is deallocated only after the program dies. So it's a good way to sort of like keep things around in case your workflow demanded this without losing them. So the question is, why do I do all this? As I said, part of my work requires that I combine things from different languages. So I kind of view Perl as the Lord of the Rings. In my work, it's the one ring that rules everything else. And that's how I would like to show you, like some toy examples of why this behavior or availability of memory management is useful. So in the next few slides, I will do the following simple stuff. I will use Task Manager to allocate a buffer, initialize it with random numbers on the C side, create a view of this as a PDL ND array, so I can use the Perl data language to sort of process that region. In particular, I will sum those numbers using PDL and give you the result. Um, I will show you how you can destroy the view of that buffer in PDL, but still keep that memory region around, and then sum the same numbers using assembly. So in the next few slides, you're going to see how one is able to use the objects of Taskman Manager to do multi-language applications. So on the left-hand side, I allocate I want a region of about 10 million doubles. Um, I tell Taskman Manager to give me access to this buffer. Then I call a C function called generate random W array. I mean, just like a stupid name. You just go on C space without memory region. You just fill it with random numbers. Then you use a function called mknd array. This is actually a port from PDLC API that allows you to generate views of random buffers in memory as PDL objects. It's actually an advanced topic when you do PDL programming, but I think it's a very useful utility to have, and I'll probably put it in another module. And then I do a sum of the numbers with PDL. That's a simple command if you are using the Perl data language. Then I undef the PDL variable, and with the same region that it still exists within my program, I just sum it in C and then sum it in assembly. So you're going to see examples of interfaces with those languages too. One of the things that became immediately obvious to me as I started playing with this is that this approach of the task manager that just gives you 64 bit integers that point to that are memory addresses, is that it's very easy to write pass them around in programs that are written in assembly. So I do quite a bit of assembly for handling biological sequences, because the modern x86-64 assembly comes with vectorized instructions that make the the vectorized execution of various operations extremely efficient. So I don't even mess with C nowadays anymore. If I want to do something very fast, I just flip to assembly. The problem is assembly is extremely painful to interface with other languages, especially because it has no easy facilities to allocate memory. You have to do syscalls, just get buffers, and then you lose all the abilities that memory managers give you to properly prevent fragmentation of memory and stuff like that. However, once you have something like the task manager, you get your area of memory and boom, you pass it to assembly like this. This is like one of the cleanest way I've seen to call assembly code from any language. Um, Once I have the buffer, the inline module converts this scalar value into a 64-bit integer, pass it to assembly, and then the sum is done. Interfacing with PDL was actually the most, it took the most effort, to be honest. The reason being is that the PDL itself is an extremely sophisticated piece of software, and it doesn't want to leave things to to lag. So it's not as easy as passing a 64-bit integer. But the major reason to consider or like interface with PDL is that it's extremely easy to write algorithms in it. Like the first talk of today's conference actually showed how easy it is to write very sophisticated numerical calculations in PDL as opposed to C or some other language. So I really wanted to be able to support that. The nuance here is that you must take ownership of the distraction and the allocation of the memory, so that the PDL memory manager doesn't do it for you, in which case you have lost the buffer that you worked to create. Oops. So this requires a generic C code, which it's generic enough to be wrapped into into a module, which I intend to do later in the year. You can find this code into the PDL API, so I just like wrapped it with inline C. C itself is extremely easy to interface. As I said, you just pass it as a pass the buffer as an integer type, and then you convert it internally using the uint ptr type in C. And when you do all those things, you end up like being able to sum 10 million doubles in using PDL, C, and assembly, and you get the same results. So what is the summary and some future directions? Task Manager is a simple Perl module that can facilitate the management of memory regions. It can use any allocator that can return an address to a memory, so basically any allocator that you can get your hands on. It controls the life cycle of allocated regions using reference counting, which fits very well with how Perl does things. But since it can tag objects for delayed distraction, you can use it to implement an on-demand garbage collector. I've not thought about a mark and sweep strategy to allocate regions, which is similar to what Go does when it manages memory, but it's certainly a possibility. I have found it rather easy to generate views of memory for containers for other languages or libraries, such as we did for PDL. In the context of my work that uses, that has to use assembly, it has made writing assembly or interfacing to assembly code extremely easy, since I can use Perl to generate the high level data flow of the program, including the allocation of memory, and then just call assembly as leaf functions for my work. In wrapping up, I would like to acknowledge EDJ, also known as Mohawk on IRC, who reviewed one of the first drafts of the paper and made some useful suggestions about the interfacing to PDL, and the organizers for putting this conference together. Thank you.
Thank you, Dr. Christos, for another mind-blowing use of Perl. In fact, I'm pretty sure that, as you have said before, those are things you were never meant to do with Perl.